Hi all, I just want to do a short video about Bayes' rule. And so we have this Bayes' rule. So it says if B1 and B2 are mutually exclusive, that means that they can't happen at the same time and the sum of their probabilities is 1. Then for any event E, the probability of B1 given E is equal to the probability of B1 times the probability of E given B1 divided by the probability of B1 times the probability of E given B1 plus the probability of B2 times the probability of E given B2, which is a mouthful. Um, and I think that, notationally it might be a little confusing to think about, but I wanted to do this quick exercise to show that we can use Bayes' theorem or we can fall back on what we've already discussed, which is the hypothetical thousands table. So I want to start with this example. It says internet addiction has been defined by researchers as a disorder characterized by excessive time spent on the internet, impaired judgment and decision-making ability, social withdrawal, and depression. The paper, The Association Between Aggressive Behaviors and Internet Addiction and Online Activities in Adolescents, and the Journal of Adolescent Health, describes a study of a large number of adolescents. Each participant in the study was assessed using the Chin Internet Addiction Scale to determine if he or she suffered from internet addiction. The following statements are based on the survey results. So here we have 51.8% of the participants were female and 48.2 were male. 13.1% of the females suffered from internet addiction, while 24.8 of the males suffered from internet addiction. So we have these events. We said F is the event that the participant is female, and M is the event that the participant is male. I'll note that here we have the participant of male and female are the mutually exclusive events, and then the I is the event that the selected participant suffers from internet addiction. So I want to determine the probability of F given I. So the probability that that it's a female given that they have an internet addiction. And so I have the information for the other way that if they have an internet addiction, I know that they're given that they're female, but I don't have this direction. But I can use a hypothetical thousands chart to think about what that would mean. So here's my chart, and let me just label my pieces. So here I have female and I have not female, which are my mutually exclusive events. And then I have the event I, internet addiction, and then not I. Sometimes you'll see a little I with a complement as a superscript for it, or sometimes you'll see the tilde. I think the notation in our book is the I with a superscript of a C for the complement, so not internet addiction. I just wrote not to be very clear. And then we have our total. So it's a hypothetical thousands table, so I know that the total should be 1,000. Going back to, let me zoom out maybe a little bit so you can see it. So I know in the study, 51.8% were females. So in our thousands chart, I could say the probability of females over in this total is 518 females. Not F is 48.2, or you could subtract from 1,000. I have 482 males in my study, or not females in the study. The other pieces I don't have, I just want to note really quick that this here is F intersection I. So it says female and has an internet addiction, which we don't have that information, but I know what percentage of the females have internet addiction. And it says 13.1 of the females have internet addiction. So of these total set of females, I know that 13.1% have an internet addiction. So the computation here to find the intersection, I can say 0.313 times the 518 will give me the total in the intersection with internet addiction, right? We can use subtraction or computation to find out the other. So I'm just going to do subtraction to find out the ones who do not have internet addiction. So that is our 518 minus the 68 that we have here. If we want to look at the males, it said that 24.8 of the total males suffer from internet addiction. So 24.8% of the 482. So here my computation I have for this box is 0.248 times the 482, which will give me the total number of males that suffer from internet addiction. Again, the subtraction will give me here, because we're talking about the total is 482. So 482 minus the 120 will give me the total who do not suffer from internet addiction. Using a quick sum, we can find out the rest of those. So the 68 plus the 120 will give me what belongs in this box. And the 450 plus the 362 is what we have in this space. And just a quick check when you do a hypothetical thousands question would be the multiplication. So this here says determine the probability of female given that they have an internet addiction. So we're just talking about the people who have internet addiction. What's the probability that that person is female? So the probability of female given internet addiction is the 68 females in the internet addiction line, and my computation is about 0.362. So about 36% chance that the person is female given that they have an internet addiction. Any questions on that? I mean, I can't really ask any questions, but feel free to reach out if you do have questions about this. I want to make a distinction to what this is asking, what this is telling us right here. Let me do an insert text box. So right here, this 13.1, this here is the probability that we have an internet addiction given that they are female. Because it says this one's equal to the 0.131. Make that a little bit smaller. It's going to drive me nuts. So the probability that they have an internet addiction given they're female is the 13.1%. Again, which differs from the probability that they're female given that they have an internet addiction. The probabilities will not be the same. Order matters when we talk about this. Let's look at the same problem using Bayes' rule for that. So this is the same question, and we have Bayes' rule here. And so my B1 and B2 are female and not female, and my event is internet addiction. And so I want to use Bayes' rule to do that computation. So for Bayes' rule, I'm going to fill in what I have. I'm going to fill in what I have. And so the probability of female given that they have an internet addiction. So probability of female from the question is 0.518. The probability of internet addiction given female is the 0.313. The probability of female, those are the total female, is 0.518. And the probability of female given internet addiction given female is the 0.313, and then the probability of not female, so that's male, is 0.48, and the probability of internet addiction given male is the 0.248. And so we have our probability. This becomes like a calculator problem you just compute. And it's exactly the same as what we got up here, the 0.362. So if you have a clear understanding of what conditional probabilities mean, in particular, what the denominator is referring to when we talk about conditional probabilities, you don't really need Bayes' rule, but I think sometimes students like formulas, and so the formula is here and feel free to use it. I am indifferent whether you decide to make a hypothetical thousands table. Some of you might have seen a Venn diagram, which gives us the same information, or Bayes' rule to compute conditional probabilities. Feel free to reach out if you have any questions, and I hope this helps you for the practice problems that you will do next.